We're going to start with Nathan Finney. So he is at Columbia University studying micro and nanoscale engineering. He's advised by Dr. James Hone. He's in his 4th year as a fellow, and he did his practicum at Lawrence Livermore National Laboratory in 2016. Today he is going to tell us about some of his research on the crystal symmetry tuning in graphene-boron nitride heterostructures with coexisting moire superlattices.
Okay, thank you very much for the introduction. Yeah, my goal is to convert this mouthful of a title into something that resembles understanding, hopefully. So to do that, I'll start by talking about allotropes of my favorite element, really everyone's favorite element, carbon. Here we have diamond and graphite. And we can see that diamond has basically this network of tetrahedrons, carbon bonded by sp3 bonds, which has this octahedral symmetry. Inside this network, we see the conventional unit cell that contains 8 carbon atoms. Graphite, on the other hand, has this sp2 bonding in plane, and it belongs to the D6H point group, and it has a unit cell which contains 4 carbon atoms. Okay, so we see that these two materials are made from the same element, but they have clearly different structures and symmetries, and therefore they have different properties, vastly different properties. Diamond is hard, transparent, and electrically insulating, and graphite is soft and slippery, opaque, and electrically conductive. Now, if we take graphite and we isolate it down to the monolayer limit, we get another allotrope of carbon called graphene. Shown here is a picture of graphene on a thin film of glass on top of a silicon wafer. And you can see that this is an optical microscope image. You can actually see this atomically thin layer when the interference conditions are right. Graphene also has sp2 bonding, similar to graphite, and it is also part of the D6H point group. It is inversion symmetric, which means that if you swap the xy coordinates of any atom inside of a unit cell, you get the exact same identical picture. Graphene is kind of a wonder material. It has all these amazing properties, including it's very stretchable. You can stretch it up to 20% of its original length before it breaks. It's 100 times stronger than steel. Its breaking strength is around 130 gigapascal. It is relatively transparent, even though it resembles graphite in structure. Because it is so thin, most of the light transmits through. But it has a very sort of flat response in its absorption. So any energy above 0.5 eV is about absorbed at 2% per layer. It's an excellent electrical and thermal conductor. It's all surface, so if you functionalize it, you can make it very sensitive to the environment. And it's relatively easy to harvest, most famously by taking Scotch tape and peeling off layers and basically mechanically exfoliating it into the monolayer limit. So because it has all these amazing properties, this motivates to ask, can we tune these properties? And the knob that we specifically chose to tune was the symmetry of the material. To understand this, we're going to go into like a simple physics model. If you do a tight binding approximation for graphene's band structure, this is the energy dispersion relation that you get. You basically have 6 K and K prime points inside the first Brillouin zone. Shown here is the block wave function in the 2-atom basis. We have A and B sublattices and the Hamiltonian. If you solve the eigenvalue problem near the K points, you get a linear dispersion in energy versus momentum. And you can see that the bands actually cross at this so-called Dirac point. And this is where the density of states is 0. So basically, everywhere except at that exact dimensionless point, this is electrically conductive. Now, I said we want to mess with the symmetry of this. So let's just look at this toy model in which I have imposed an energy difference at the A and B sublattice sites. The major change is that the Hamiltonian now includes these diagonal terms matching this separation energy. If I then go solve this eigenvalue problem again, my linear dispersion gets these little curved points at the ends of the band edges. So this Dirac crossing is no longer protected, and we now have this forbidden energy zone. So a gap has opened up. And we've basically turned this thing that was originally an electrical conductor into an insulator. OK, so the question is, how can we do this? How can we modify each atomic registry in some way such that the symmetry is changed identically to a different symmetry group? So to understand this, let's look at another toy model. Here we have a 1D chain of atoms, just say they're carbon atoms, and I've simplified their periodic potential into these square wells. We see that in the 1D case, we have this mirror symmetric unit cell, and if we make this electron conduct through the unit cell, it's going to feel this periodic potential. And then strictly speaking, this is going to obey Bloch's theorem, where the spatial component of the electron's wave function is modulated by another wave function that is translationally symmetric over translations equal to the unit cell length. And so for graphene, we can take advantage of the fact that it is atomically flat, and we can put it in contact with another atomically flat material that has the symmetry that we want to inherit. And so here we have another pretend material. It has mirror symmetry broken. So even if this electron is tightly bound to the carbon lattice, it's still going to feel this modulated potential with this different symmetry. And so we imagine that it's going to sort of dance along with its original motion perturbed, adopting the new lower symmetry of the system. OK, so how can we do this in practice? Well, fortunately, there exists a material that is also organized into these hexagons. We have boron nitride. It's alternating nitrogen and boron atoms, which do have this slight potential energy difference at the atomic sites. The other neat thing is that it is a good dielectric, so we can actually use it to encapsulate our graphene layer and use it as a dielectric for a field effect transistor device. It's also known to screen the electrostatic conditions of the environment, so it actually makes the graphene's electronic behavior a lot cleaner. This has been known for about 10 years. But there is a problem, which is these two materials have different lattice constants. So there's a slight lattice mismatch shown with this delta sign here, which means that we won't get perfect overlap of the carbon and boron atoms. Okay, and so if we take a piece of graphene and put it in contact with a piece of boron nitride, we get this geometric interference pattern, or so-called moire pattern, which has periodicity characterized by this lambda term, this moire wavelength. And you can think of that as basically the lattice constant of this superlattice that is formed by the combination of the two materials. Now we can also change the scaling of this superlattice simply by rotating the layers against each other. Okay, so we can see that at large angle, we have small unit cells. And then as these corners pass against each other, the size is maximized. And so the dispersion for the size of this wavelength versus the twist angle looks like this. And this is a real effect. You can actually image these superlattices of graphene on boron nitride with STM. And so here we have, basically this is a spatial local density of states map provided by an STM scan. And at small twist angle, we have large unit cells. Large twist angle, we have small unit cells. OK, so then to understand how we're going to probe the symmetry in the system, I didn't use STM. I used field effect transistor device. So let's just look at the field effect response for graphene. So again, here's the band structure of graphene with the simplified schematic here and the Dirac point. Now, if I imagine I tune the Fermi level by basically changing the carrier density by applying an electric field, I can sweep through this Dirac point where supposedly there should be no conduction. And indeed, that is what happens. If I sweep some gate under the graphene, which changes the carrier density, as I pass through zero energy, or where the Fermi level should be, I see this spike in the resistivity. And if the Fermi level was perfectly straight line, I would sample this point, and I would get a Dirac delta function. But because I have finite temperature, there's some smearing of the Fermi level, so I'm going to sample states from the conduction band to the conduction band to the valence band, and it's going to sort of broaden this peak. OK, so then if I combine, again, the boron nitride with the graphene, I actually end up with this periodic potential, as I showed you with the 1D case, except now it has this D3H symmetry. The graphene band structure evolves to have these replica Dirac points, which is due to zone folding, shown here in this schematic. I'm covering the laser, that's why. Shown here in the schematic is that I get these replica secondary Dirac points. I'm going to label these primary and secondary now. And if I sweep my energy by changing the gate again, I'm going to sample the original Dirac point, which I can see here, but I'm also going to sample these new points. And so I get this secondary peak in the resistance versus gate spectrum. Okay, this peak contains the information about the symmetry of the system as well as the superlattice. When it shifts, it's basically telling me information about the wavelength of the superlattice as well as the angle, according to the dispersion that I showed you on the previous slide. So what about that symmetry? So if we look at this picture, we can see three clearly different colors. We have white, red, blue. Okay, and they represent these high symmetry points, these different stacking orders. And so we can see that certain points do have near perfect atomic registry of the carbon atoms and the boron and nitrogen atoms. But at other places, we do not. And so obviously, the picture is different than the 1D example I showed. The superlattice itself actually has D3H symmetry, mimicking the symmetry of the boron nitride. OK. So the test is basically, does this system open the gap as we expected it to in our simple toy model? And the answer is yes. So if you do thermal activation measurements on just graphene aligned to a single layer of boron nitride, we can see that as a function of the twist angle between the two, we get an increase in the gap size in the forbidden zone. Okay? And so actually, we get to update our picture of what this reconstructed band structure looks like to include these gaps. Now, I should note that this is a well-understood phenomenon. I have tuned the symmetry of graphene from D6H to D3H, but that is not a reversible process. I cannot easily just unpeel the graphene from the boron nitride and restore it back to its original symmetry. Our goal is to actually tune the symmetry. So the way we propose to do that, or the way we thought to do that, is basically combine another layer of boron nitride and try to get these two layers to impose a potential that adds that might be able to sweep us in and out of the two symmetries. Okay, so just taking a look, some interesting things happen. The picture gets very crazy. Not only do we have two coexisting geometric interference patterns, but we also have a geometric interference pattern of the geometric interference patterns. Okay, so we've made it very complicated for ourselves, which is what we love to do. Okay, so we need to break this into to more questions. We want to know what happens near perfect alignment to sort of answer our original questions about can we tune the symmetry. But there's also interesting things that happen at slight misalignment. So we might be able to learn something about the coexistence of these two superlattices. OK, so I'm just going to go over two definitions here. So just going to define theta B and theta T as the angle between the bottom BN graphene and top BN graphene, which I'm just going to refer to for the rest of the talk. OK, and the device that we built to be able to study this is standard graphene on BN spacer over a graphite backgate. The graphene is shaped into a graphene hall bar. And then we made sure in the production of this that the graphene was aligned to the bottom layer of boron nitride so that we wouldn't have to worry about that moire. It's just going to be held constant. And then we put on top of that a rotatable BN structure over the channel where we can measure the resistivity. This top piece is rotatable, okay, by pushing on it with a atomic force microscope in contact mode. And just to try to help us imagine what that looks like, I basically have an AFM tip, and then I bring it into contact with its top BN rotator. I push, BN rotator rotates, I push, BN rotator rotates. And then basically, when I do an AFM scan of this picture, I can use an on-screen protractor to measure the angle, the angular displacement, and corroborate that with the measurements I take. Okay. This is a sequence of AFM scans before and after pushes. So this is one of the rotators. You can see this sort of, this is a phase image. So the contrast is basically just showing difference in phase for this AFM and tapping mode. I'll point out the scale here. The channel is actually just a micron wide. Human hair is 70 microns. So this device is very, very small. So it's kind of amazing the amount of control that we can exert. Oh, and then this goo is just residues that are left over from the production of this device. This was an early device that was sort of dirty. So actually, we discovered that these rotators are also able to sort of sweep and clean up the channel. They kind of expel the residues, which is kind of a feature, a nice feature. OK. OK, so if we have the top layer misaligned to the channel, we see our standard gate sweep signal. So just what I showed you earlier. And just to remind you again, when I sweep the gate, I'm changing the carrier density in the graphene. And really, I'm sampling this energy versus momentum diagram by tuning the Fermi energy. Okay? And then the resistivity is just measured by a simple Ohm's law relation, measuring a voltage drop in the channel. OK, now I take my AFM and I rotate it until I see some significant change in the sweep. So I'm labeling this 0 degrees. I see some maximum interaction. This is sort of a tentative label. And then if I rotate back to 60 degrees, I see a slightly different peak, it's similar. But basically, it's a suppressed enhancement. So at 0 degrees, I see this enhancement of the peaks, and then a suppressed enhancement at 60 degrees. OK, and then I sit at the AFM for almost 2 days straight and take a very dense map of field sweeps at various angles. So this is over a full 360-degree range. And I track the heights of these resistivity peaks. And we can clearly see this equivalency over 120-degree rotations in the response, where we have sort of shifted by 60 degrees. We have this enhancement of the resistivity, and then we have this suppression. And so just looking at this picture, we can imagine, all right, so if I'm sampling a gap, the resistance should go up. This is all at room temperature, so there are other important considerations, like what is the mobility of this band? What is the actual curvature of this band? These are all things that determine how the electrons will conduct. And so to really understand how the band structure is going to evolve, we actually have to take the system down to low temperature to try to narrow this Fermi level. OK, so this is what we do. So we cool the system. So we cool the system from room temperature down to about 1.7 Kelvin. I'm tracking now the conductivity, which is just like the inverse of the resistivity, basically, versus the gate sweep at near the primary Dirac point and the secondary Dirac point at the top BN angle equal to 0 degrees and the top BN angle equal to 60 degrees. And so we can see that actually at 0 degrees, we're much more thermally activated. We see a larger change in the conductance, or in the conductivity. And if I take a line cut, so basically sampling points, plotting the conductivity versus the temperature, I can do an Arrhenius fit to extract what the thermal activation gaps should be. And so as a function of angle, I can plot how these gaps change. And I can see that clearly at 60 degrees, I have this enhanced gap. I'm sorry, at 0 degrees, I have this enhanced gap. And then at 60 degrees, I have this suppressed gap. I'll just quickly point out that this gap in monolayer graphene, this is a record gap for pristinely produced graphene moire superlattices. So this is actually 60 MeV, I think, is in the far infrared regime. So this device is sensitive to the types of light signals that might come out of the center of galaxies or human bodies. OK, so looking at this curve, we can now go back to our consideration of symmetry. So in the case where the top BN is aligned to the bottom 2 layers, we think again about the atomic registries, and we say, OK, yes, we have this point where we have near perfect atomic registry, nitrogen over carbon over nitrogen, boron over carbon over boron, and we're just going to imagine, OK, well, basically, I'm doubling the potential that we felt in the first case. So this is almost exactly equivalent to what we saw with graphene aligned to single layer boron nitride, but it's doubled. OK, so here we still have this 120-degree rotational symmetry, and the inversion symmetry is broken. But at the 60-degree case, I now have this equivalency across the unit cell. So boron over carbon over nitrogen, if I just flip the xy coordinates, nitrogen over carbon over boron is identical in terms of how the potentials add. And so I've actually then just taken, by virtue of tuning these superlattices, a system that was D3H symmetric and made it D6H. And because I can continuously rotate the top layer, this is tunable. It's totally reversible. So this is quite amazing. OK, and then if we're going to draw a cartoon of how we think the band structure is evolving, so here's the sort of nominal graphene aligned to single layer of boron nitride. When it's doubly aligned in this favorable condition where theta t equals 0 degrees, we get this increase in the gap. And then at 60 degrees, we sort of return to this picture where maybe the Dirac crossings are protected. OK, so then on to the second question, the complicated case where the top boron nitride is sort of slightly twisted. So here are field sweeps again. Theta t equals 0 degrees, 30 degrees, 60 degrees. But now I've included some very small offset angle for the top BN. And we can see that the peak is not quite the same magnitude as the other two peaks. It is still enhanced. But more importantly, it has shifted, which basically means that there could be two peaks, maybe that are working in concert to generate this peak. Resistance peak don't add in superposition, but they might smear together and at room temperature, so you can't quite see the two original peaks. So again, we take this system down to base temperature. Okay, this is what the sweep looks like. But before I talk about the sweep more, I just want to, again, make sure that we think about this. The bottom boron nitride in graphene has this set moire pattern. The top boron nitride in graphene has a different moire pattern. Okay? And the two are basically periodic potentials that should add in superposition. And when you add them, they look something like this. And so the question is, do these this was an open question at the time, do these two moire patterns sort of convolve with each other and make a new structure, or are they really just acting in superposition? And the answer is they coexist, and they coexist in a way that actually exactly follows the dispersion that I'd normally use. And so they really are just like two independent periodic potentials that are independently tuned as we would expect. There is kind of an interesting detail here, which is, OK, fine. Now I basically have two gaps down in the hole band for the graphene. But they're pretty close to each other in energy. And so I'm actually taking two forbidden energy zones and sort of squeezing them together. And so one potential thing that could be happening here is we could be creating this, what's called a flat band condition, where I basically have a resistance peak from the first moire and a resistance peak from the second moire. And they're squeezing together to sort of flatten this low mobility band in the middle. Recent studies have shown that in twisted bilayer graphene, when you can generate a flat band condition, you can get really exotic effects like superconductivity to appear. So this could be a novel system or a system like it where we could get some sort of tunable flat band condition and then tune a system in and out of superconductive states with like a nanomechanical switch. OK, so in summary, we've achieved reversible symmetry tuning in BN-encapsulated graphene heterostructures. And we observed these emergent features of multiple coexisting moire patterns. Looking to the future, the whole story is not just graphene and boron nitride. Obviously, there are many other species of 2D materials that we could put in combination with each other to try to exploit symmetry tuning specifically. We can also imagine perhaps some sort of nano-electromechanical system where I can use voltage signals to rotate the piece or actuate the piece rather than an AFM, which would make this very portable, and maybe you can actually include it as part of like a sensing scheme for other applications. OK, so with that, I just want to acknowledge some of my collaborators. The top row are people who specifically worked on this project and are part of the paper that we wrote about it. Matt helped me with the analysis and the data collection and significant ideation along the way. Lithu helped with early fabrication procedures for the devices. Corey and Jim are the faculty advisors. And Kenji and Takashi supply us and many other groups around the world with high-quality boron nitride crystals. On the bottom row, we have Rebecca and Xian Jian, who wrote a really seminal work on twistable BN graphene heterostructures. So their device technology is basically what we adopted to be able to achieve what we were able to achieve. And then Xiaowen, who helped significantly with some technical difficulties that I was experiencing along the way. And last but definitely not least, I just want to thank all the administrators at CREL and the national labs and NNSA, as well as the alumni who support us and inspire us. This has really been such an incredible opportunity for me, and I cannot thank you enough for it. Thanks.